All right, so where did we leave off? Okay. So a couple things before we get started. We got that problem set. We'll kind of see how today's class goes. I might go through the slides a little bit out of order based off of what I want you to do for the quiz and what I want you to do for the problem set. So I think my focus today is going to be to get through all the material so that you can complete that problem set. I don't know if we'll quite get through all the material you need for that first quiz. And so that first quiz due date, I might push a little bit for like further into the future. All right. So we'll see where we end. I'll kind of mention at the end of class, kind of depending on where we get, what those due date changes might look like. But that's what I expect. Okay. So here also have one thing I want to add in here today, which will be, we'll eventually get to this first in-class quiz. So go up here. I'm going to unpublish it for a second. Let's see. Maybe people have already started this. Shouldn't have. So I'll make sure I have this kind of set to go. Oh, that's why. I didn't change the due date to be today. And then we'll make sure that once we get to that point, should have the access code set correct. Let's make sure. So it looks like it reverted some things that I'd done. So let's make sure this is saved so that when we get to this point, we'll be good to go. Okay. So we'll kind of use this in-class quiz later on. So don't worry about opening it right now. I'll kind of give you the access code once we get to that point. But we left off talking about kind of normal distributions. Yeah.
You wanted to know.
Oh, yes. Thank you. So when we get to Stata, I'll kind of show you guys. In fact, we can do it right now. A common issue that I'm seeing happen, and I think it has to do with like software updates. And then if you like close out your restart your computer, if you go to open up Stata, it'll just like give you the spinning wheel of death. So if that happens and you've already downloaded Citrix, going back here and activating it, kind of reactivating it may then prompt you for your IU email. So usually if you don't, it'll send you to this thing where it says like enter the URL and it doesn't accept your IU email address. If you go back through and activate Citrix, usually if you've downloaded the program, it'll automatically go to asking you for your IU credentials, your username and password. If you're operating Citrix through kind of a web browser, you'll run this and then it'll kind of prompt you for, actually usually it'll take your IU credentials from already being signed in and kind of automatically kind of pull the program open. But if you're running this off of the Citrix Workspace app, you may have to kind of go to activate this and then it'll kind of re-prompt you for that IU. So I had someone stop by yesterday and that's exactly what happened. Okay. So I think it has to do with like software updates on the technical side of things. Okay. So thank you for reminding me. Any other questions before we kind of get started here? Okay. So we left off, and I'll go through some of this material pretty quick today. Hopefully it's a lot of review, right, from what you've done in your other stats courses. So we talked about variables that we can calculate the mean, we can calculate the standard deviation, and even though they look normally distributed, in order to compare across variables, what did we want to turn that normal distribution into? Add an additional word to normal distribution. Standard normal distribution, right? We can then use these Z tables to start to find what's the likelihood or probability we see certain values based off of what values we see exist in that data set. So we went through some examples. We said, if I condition on things, maybe I still have two what looks like pretty normally distributed data sets. So this was like some CrossFit data I think I pulled, and I was like, oh, it's a nice example for class. It's got two like pretty normal distributions, right? Now, the normal distribution for males was shifted a little bit. So even though they look like they have about the same variance, one of those groups had a higher mean. We kind of worked through some examples last class where we thought about if we condition on certain things, maybe the mean, right, would shift that distribution to the left or right. Or if I condition on certain groups, if the variance changes, if the variance is higher, our distribution is going to be what? More. What does the variance tell us? How varied the data is? So a higher variance means that I'm going to have a wider distribution, right? Or fatter tails. So we then kind of talked about, we can turn these into z-scores. Well, looks like I left it off here of this slide. So we'll kind of go just to remind ourselves. How did we turn any kind of normally distributed variable? So maybe this variable has a normal distribution, and it's got some mean, and it's got some variance. Okay, that's usually how we would write this. If I want to turn this into a standard normal distribution or a z-score, we said I'll take that original x variable and I'll do what? Subtract the mean, right? And I divide by the standard deviation. This gives me a kind of nice normal distribution for these z-scores where I have the mean is going to have a z-score of 0. And when we divide by that standard deviation, it gave me a variance and a standard deviation of 1. Okay. So once I have these z-scores, I can start to do some interesting things. Okay. So if I start out and I've got some normally distributed variable x, right? It has a mean and it has some variance. This variance could be, I don't know, 20, and the mean, we make up some values, right? If I turn it into a standard normal distribution, right, that mean should have a z-score of, or the kind of mean of this standardized variable will always be, whoops, 0. Okay. So let's say I look at the data and I see a certain x value, right? Let's assume that the x value I see is 1 standard deviation above the mean. It doesn't matter if I've got human height, test scores, whatever the variable is, it could have any mean, any variance. When I turn this into a z-score, what am I going to do? I'm going to take that x value, so that would be the mean. It was a value that was 1 standard deviation above the mean. If I standardize it, what am I going to do? I'm going to subtract the mean and divide by the standard deviation. Now, we said one interpretation of these z-scores, it's essentially the number of standard deviations away from the mean that x value is. So why is that the case? Well, if I take any value from any variable and it's 1 standard deviation above the mean, when I subtract the mean, what happens here? This cancels. What am I left with? The standard deviation of the standard deviation. So I would always have a z-score of 1. Any variable I'm looking at, if the value for x for that variable is 1 standard deviation above the mean, when I convert this into a z-score, it's always going to have a z-score of 1. So I then start to think about, what are these distributions telling me? Okay. Well, the distribution, what did we say is on the y-axis? I get lazy and don't write it a lot, but it's telling me the probability that I see that specific x value. So here, it's like the probability that this variable x is equal to 20, 25, some specific value. Well, essentially down here, it's telling me the probability that the z-score is equal to a specific z value. So if I'm thinking about a z-score of 1, when I go to our standard normal tables, what we'll end up seeing is, how could I get the area under a curve but below a certain value? I would essentially need to do what? Starts with an I. How do I find the area under a curve? Integrate, right? So I would integrate that function from essentially negative infinity up to 1. That would give me the total area under that curve. Well, if these represent probabilities, if I take the probability I see negative infinity, all these different values, what that's really telling me is, if I integrate this function, the area under the curve is the probability I see that z-score be less than whatever z-score I'm interested in. In this example, we had 1. Okay. So that gives us, what would that represent? Not a single probability, but if I'm adding all these up, I would call that a, starts with a C, cumulative probability. The probability I see any value that's one standard deviation above the mean or anything below that. Okay? So we'll start to use this idea that if we can convert any value into a standard normal distribution, into a z-score, I don't have to just find the probability that I see a value below a certain value. I can find the probability I'm in between two values. Okay? So if we do this, right, we can use this standard normal table. Now I'll go through this kind of quickly, and then I'll show you where I'm getting these values from. So it ends up being true. If I ever have something that's 1.29 standard deviations below the mean, when I integrate that standard normally distributed function, I'm from negative infinity to negative 1.29, I will always find the same value. It's the same standard normal distribution. And the value I'll find will be approximately 0.1. So we'll start talking about today some of our benchmark values that we usually compare to are, well, what's the likelihood something occurs? Some nice cutoffs are there was a 1%, 5%, 10% likelihood it occurred, or probabilities of 0.01, 0.05, and 0.1. Okay. So how did I come up with this probability, right? Well, essentially, there is a function for the standard normal distribution, and if we integrate that function up to a z-score of negative 1.29, I'll always find the same value. Now, we're not going to have to do that integration. People have already done that work for us. So I think I said that right in the previous slide, okay? So that's where I have this table, right? Now, in practice, we might use this Z table initially, like for the first quiz or so. Eventually, we'll start to get to where we can do this in Stata, and we don't have to worry about it. But for now, we have to walk before we can run, okay? So the way you use this Z table is essentially whatever Z value you want to find the cumulative probability of, the probability I see this value or anything less, you'll look up the first decimal in this column, okay? You will then look up the second decimal in whatever row that you're looking at. So we're always going to have to round these z-scores to the second decimal. If we wanted to integrate this function, technically, we could do this out to whatever decimal we want. But we're just going to kind of use the table instead of doing the integration. So if I have, let's say, that z value of negative 1.29, well, this table only gives me the negative values. We'll see why this doesn't really matter ultimately. So if I go down to negative 1.2, and then what's my second decimal? 9. 1.29 gives me that probability, or the area under the curve is always going to be 0.0985. Okay. So whenever I find a z-score, or wherever I see a value for a variable that's 1.29 standard deviations below the mean, the probability I saw something that far away from the mean, or anything even further, right, anything even less than 1.29 standard deviations, would always be 0.0985. Okay. So that's how we use this table. Hopefully, did you use this in your other stats courses? Did you guys use these tables? Hopefully, I'm seeing a lot of head nods. Yes, I taught 370, so if they didn't do that, they should have. Right? It should be a big part of that course. Okay. Now, the other half is going to be the positive values. Now, I said we don't really need this, right? So let's think about why. If I just told you, and we can look it up in the table, that when I'm looking at z-scores, the probability I see something 1.29 standard deviations or anything below that, that probability or that area is always 0.0985. What if instead I wanted the probability that I see a z-score above positive 1.29? Well, now what area am I looking for? This is where drawing it out helps sometimes. Now I'm looking for the probability I see 1.29 standard deviations above the mean or anything greater. But what is true about this distribution? It's centered around what value? The mean, once we standardize a variable, is always 0. So this is a symmetric distribution. So the area to the left of negative 1.29 should be the exact same as the area to the right of positive 1.29, right? That should always be the case. If this is a symmetric distribution, if I know the probability of being less than the negative value, I would always know the probability of being greater than the positive value. Okay? So in practice, if I had any two values, right? So let's say I did something like this, where my original x variable, I said, okay, it's got a mean of, I don't know, I can just make these up, 78, right? And let's say, just to make this kind of easy, so let's say I look at, I want the probability, I see something in between 80 and 77. Or I guess here, I didn't draw this to scale. Let's do 76, so it looks a little bit more to scale here. So I don't want the area to the left or the right of a certain value. I want the probability that if I selected someone at random, I guess this doesn't make sense for human height, but maybe it's some test score, right? Maybe this is the average score in this class. So if I select one student from my class, I know the mean on an exam might be 78. What's the probability if I selected one student at random that I see their score be in between 80 and 76? Well, I don't have this distribution, but I can always turn a normal distribution into a standard normal distribution, okay? So let's say for the sake of this example, I've actually got something that's symmetric. So this will make it a little bit easier for me. Let's say my standard deviation, for the sake of this example, is 2. What would the z-score of my mean be? 0. How many standard deviations above that mean is 80? Well, if the standard deviation is 2, how many standard deviations above the mean is 80? 1. So the z-score would be 1. The z-score tells us the number of standard deviations above the mean. If I wanted to prove this to myself, I would take that value of 80, subtract the mean, divide by the standard deviation. Sure enough, the value I get is 1. Now, if I do the same thing for 76, kept the numbers a little easier here. If I'm 2 standard deviations below the mean, not 2 standard deviations, sorry. If I'm 2 away from the mean, how many standard deviations away am I from the mean? Well, if the standard deviation is 2, I would be 1 standard deviation below. So I want this area in between. How can I find that? Right? Well, if I took the probability that I saw something less than -1, and I subtracted that from the probability I saw something less than 1, what am I left with? The area in between. Okay. So I could go to my table. Here I have the Z table pulled up, and I put this on Canvas for us. Let's see, where is it at? There it is, right? So if I've got this Z table, well, 1, right, would be, sorry, -1, -1.00. Okay, so the area to the left of that z-score is 0.1587. Now, I could look up the z-score of 1, but I'm not going to do that to show something to you. Okay, so we just found the probability of being less than -1 was what? 0.1587. Let's say I didn't give you the other half of that z-score table. How could I find the probability of not being less than -1, but the probability of being less than 1? Well, what's the probability I see something greater than 1? If this is a symmetric distribution, the area to the left of -1 would be the exact same as the area to the right of +1. What's the area under this curve always going to be? If I select someone at random, what's the probability their test score is in between 0 and 100? 1. That's every possible value. So the area under this curve will always be 1. So if I know the area to the right of +1 is 0.1587, what's the area to the left of it have to be? 1 minus that, right? So this would be what? 0.8413. Okay. Now, if I originally wanted the probability, if I select someone at random, their test score is in between 76 and 80, I now have this area to the left of +1. I know the area to the left of -1. What would I do? Just subtract this area from the larger area, and I'd just be left with what's in between. So I have what? 0.8413 minus 0.1587. This is approximately going to be what? 0.7-ish, a little bit less than 0.7, right? So I could do this for any values, right? Turn them into z-scores. Now, they might not always be the same, right? Maybe I wanted to know the probability that's in between 76 and 84. right? Well, then I would have different z-scores. I go through the same process, but in terms of the process I use, same exact process, it's just that the values would be a little bit different, okay? Is this looking hopefully familiar to some things that you've seen before? So we'll start using the standard normal distribution quite a bit, and I'll kind of have some support as to why we're doing that, all right? But for now, let's go back to our slides. We looked up these z-scores, right? Visually, we said we can find the probability of being any less than a certain value. So let's for a second just kind of reason through this and see if by process of elimination, based off of what we talked about, what if I wanted the probability that I'm greater than a z-score of negative 2.53? So if I select someone at random, what's the probability that they're 2.5-ish standard deviations below the mean or anything above that? Well, we just said the probability that I'm less than 1.29 standard deviations, that probability was like 0.1. So if I want to know the probability of being less than negative 2.5, what's going to happen to the area in that tail? It's going to get smaller, okay? So I know that probability should be less than 0.1. Now, the area to the left is not what I'm looking for here. What am I actually looking for? The area to the right. So for that z-score of negative 1.29, sorry, we'll go back. For the area of negative to the left of negative 1.29, what's the area to the right? Well, if this is approximately 0.1, the area to the right would be 0.9. So if I go out to a z-score of negative 2.53, the area to the right of that must be greater than 0.9, right? Because I know the area to the right of negative 1.29 was 0.9. So if I go even further out, the area to the right has to be something larger than that. So when I'm thinking about a question like this, right, I know automatically that that probability has to be greater than 0.9. Which of these is greater than 0.9? Only one of them, right? In fact, why can I rule C out right away? What's the lowest a probability can be? 0. So if I get a negative answer, I know I made a mistake somewhere, right? The lowest the probability could ever be is 0. Now, why would I come up with answer B? I might have forgotten one step. You said, why would maybe I come up with the answer of B instead of, I know that it has to be D here, because we said it has to be greater than 0.9, just process of elimination based on what we already talked about. If I were to look up this value on my Z table of negative 2.53, negative 2.5, it's kind of hidden here, but 3, oh, that area to the left is 0.0057. But remember, we are looking for the area to the right. So what step did I still have to do? Subtract that from 1, right? Which is what gives us that value of 0.9943. So we can kind of, with these like multiple choice questions, we can kind of process of elimination, sometimes come up with the answer based off of what we've already done, okay? In fact, if I ever have a negative z-score, what does the probability always have to be greater than? If I'm looking for the area to the right of it, what's the area to the left and the right of a z-score of 0? This is a symmetric distribution, and the mean is 0. The area to the left and the right have to be, they're the same size. The area under the curve is 1, so each of them would be 0.5. So if I'm ever looking at a negative z value, the area to the right of it would always have to be greater than 0.5. So we can start to kind of think about, once again, process of elimination. We can actually use the z table to actually find the actual values if I didn't have a multiple choice and I just left it open-ended, okay? So just to kind of mention some of the common z-scores that we'll start seeing pop up, especially once we get to hypothesis testing and confidence intervals, are kind of the corresponding z-values, right? And the reason why is because you can kind of start to think about, well, what's the probability I see something less than 1.29, standard deviations above or below? It's about 0.9, about 0.95, about 0.975, 99, 9.995. These are like 90, 95, 97.5, 99%. The last one, 99.5%, right? These are just our general kind of benchmark values. We'll typically use 1, 5, and 10%, which would correspond to probabilities of 0.1, 0.05, and 0.1, 0.05, and 0.01. Okay. So all of this to be said, right? How could I work through an example? So let's say I had this weird example where I'm thinking about, if you haven't seen the movie Mr. Nanny, it's with Hulk Hogan. Let's say they want to release a new one, right? So they've got kind of this normally distributed variable, and it's the pounds of popcorn at this movie theater. This is kind of this is ages me a little bit. We're used to go to a movie theater, right? So I've got a mean. Usually I sell about 50 pounds, and I've got a variance of 100. Okay. If I want to know what's the probability that if I make 60 pounds of, I won't have enough. So what's the probability that demand is greater than 60? So I can set this up, and this is where I think drawing out the visual will kind of help. So I have this normally distributed variable, and I was told the mean is 50 and the variance is 100. Now, what I would start doing, because what do we need to actually turn something into a standardly normally distributed value or a z-score? I don't need the variance, I need the standard deviation. So what is the standard deviation? Just the square root of the variance, right? So the square root of 100 gives me that standard deviation of 10. So if I make 60 pounds, what's the probability that I haven't made enough, or that demand is actually higher than that? Something about economics. I produce a certain amount. What's the likelihood I don't make enough, or I'm going to have a shortage, right? Well, what we would do is we want to convert this into a standard normally distributed value. So what would a z-score be for 60? Well, I take the x value, I subtract the mean, and I divide by the standard deviation, right? So here I get a z-score of +1, okay? We've actually already looked this up in the table, so we can kind of cheat a little bit. But the probability that I'm less than 1, if I didn't want to cheat, I would then go to my z table, look up 1.00. So these kind of integer values are a little bit tricky, but if I have 1 or 2, the two decimals associated with it are zeros, right? So 1.00, the probability I see that or anything, remember the table tells you the probability of seeing that z value or anything below it. So I've got 0.8413, okay? So if I go back to my work, I just found the probability of seeing a z-score of 1 or anything below it is 0.8413. Well, now this is where I might have made a mistake. Oh, my finger didn't quite get that. There we go. All right. So we just found that probability is 0.8413. But I wanted the likelihood that I don't make enough. So what do I still need to do? Subtract that from 1, or I get what, 0.1587 if I'm doing math quickly in my head, correct? Okay. Any questions kind of over this process, or maybe something we didn't kind of throw in here that you might see? Once again, hopefully this is somewhat review of things that you've kind of seen before. Right. So we end up with that answer, right? This was an actual movie. I'm not making it up. You could do the same thing, but find the probability that it's under 40. Now here, I'll go through this kind of quickly, but without using that table, we said the standard deviation, excuse me. Oh, is this going to help me? Yeah. So what's the probability demand is somewhere over 60, but under 40? Well, we just found the probability that demand was above 60. That was about, excuse me, 0.1587. How many standard deviations away from the mean would a value of 40 be? Well, if 60 was one standard deviation above that mean of 50, how far away from that mean is 40? One standard deviation. It's just that it's one standard deviation below. So if I had the same z-score, but one's positive, one negative, the areas in the tail would be exactly the same. So I would just add up 0.1587 plus 0.1587, give me that value about 0.1 or 0.31. Okay. So, I've got some examples in the practice problem where you can kind of work through this with some different values, but this is kind of our basic, how we use that standard normal distribution to tell us things. Okay. And then here's a screenshot from that movie, which is wild, right? So where are we at in time? Okay, perfect. So let's say I want to work in the reverse, right? So we kind of already talked about when I turn a value into a z-score, this was the formula that I'm using. What if I want to back out, right? What value would give me a specific probability? So we just worked through examples where I had the X value and I want to find the probability that I see that or anything below it. So let's do a problem where instead I've got some exam score and I want to know where is the cutoff for being in the top 10% of that test, right? Maybe I'm curious about that as a student, right? Or if I'm thinking about something like the SAT or ACT, I want to end up in the top 10%. What's that cutoff score I need? Okay. So I've got the mean and I've got the variance of this original variable. How can I work backwards? Okay. So I'll draw this out for us, but we're thinking about, we have this test score. I know the mean is 72, and I was told that the variance is 64. Okay. I want to know what test score would put me, would kind of be the cutoff for being in the top 10%, or the probability that if I select some random, they're in that top 10%. So what's that cutoff score to be in the top 10? Well, if it's 10%, I know that the area that I'm looking for, that probability is 0.1. So I can use my z-table. The problem is the z-table always gives me the area to the left. So what area do I actually want to the left? 0.9. Okay. So I can always work in reverse and say, okay, I've got this z-table. Now, first of all, if I know that I want the area to the left of a value to be, of a certain z value to be 0.9, well, what's the area to the left of a z-score of 0? If it splits the distribution in half, it should be 0.5. So I know the z-score I should be using is going to be something that is greater than greater than 0, right? To give me that probability of 0.9. So instead of looking up the z-score, I know the probability. So this is where we have to do some rounding. Because if I'm hunting through these values, which represent my cumulative probabilities, looks like the closest I can get to 0.9 is in between these two values, right? So that would be a z-score of 1.28 and 1.29. If we ever end up between any two values, just by what we're going to do for this class, since we're not doing the integration ourselves, we'll always just choose the higher of the two. So in absolute terms. So if I'm in between 1.28 and 1.29, I'll use that z-score of 1.29. Okay. So I now know that from a standard normal distribution, the probability I ever see a z-score of 1.29 or anything below that is approximately that 0.9. Once again, we were in between two. We kind of had to round to the second decimal. So what I want to do is I want to work backwards. I want to know what X value is going to be 1.29 standard deviations above the mean. Well, if I take this equation, which calculates a z-score, if I just rearrange some things, I'll do the algebra very quickly here, multiply both sides by the standard deviation, add the mean, I get that cutoff score for the top 10% is going to be this. Well, I know the mean. I don't know the standard deviation, but I know the variance. So what is the standard deviation going to be? Simply the square root of the variance, right? So the square root of that variance of 64 would be 8. So I now have this. I know the z-score I wanted for that top 10% cutoff is 1.29. Now it's just a little bit of algebra, all right? So I don't know, this is going to be approximately, I don't know, 82-ish, if I'm doing math in my head correct here. If I actually plug this into my calculator, hopefully my math isn't really bad in my head and I'm actually close. So we kind of worked backwards. We found that z-score. We then plugged that into our equation. Sure enough, it's right around 82. Okay. Any questions on that process? So I can always find the probability I see a certain X value if I'm given that cutoff or X value and I want to kind of find that probability. But I can also find that X value that would give me a desired probability. It's just working in the opposite order, right? So the first examples we started with, we knew the X value from the original variable. We then want to find the probability I saw that or anything below it. In the second kind of this inverse transformation, I know the probability I want in one of those tails. I know I'm looking for the cutoff score for the top 10% or the top 20%. And I want to work backwards and see what value for the original X variable would give me that desired probability. Okay. So before we kind of move on to the next topic, if you have any questions about the standard normal distribution, standardizing variables, and we looked at how we standardize variables in Stata. The reason why we wanted to do that is because now every value, once I've standardized it, what does a standardized variable tell me? Well, they would represent what? If I standardize something, I now have z-scores. So once I standardize a variable, the value I see is now telling me how many standard deviations away from the mean that specific X value does for that observation. Okay. And then I could kind of go through this process and find, what's the likelihood I choose someone at random, I see them have this value for whatever variable, test scores, human height, whatever it is. Okay. So that's our basic setup. We're going to get a little more complicated and then do some hand waving and say we don't have to worry about this anymore, right? So we usually don't have population data. We only have sample data, right? It's a small subset of the population. So what's going to end up being true is I've got this sample. So instead of capital N, which is the population size, we'll start saying this is the size of my sample, lowercase n. I said quite often differences between populations and samples. We go from capital to lowercase letters, or we go from Greek to alpha, like our typical English lettering. Okay. So here what we're kind of assuming is that when we select any one when we select any one observation, it's independent of the fact that I selected somebody else, right? So I'll just give you a way that this is sometimes violated. Most data sets, we don't have to worry about this assumption. So like if I was interested in test score data and I just start randomly selecting student IDs, well, it doesn't matter that I selected your student ID first. The next person I select, it could be anybody else. Like those two things are independent of each other. Now, what if I wanted to collect data on birth weights? Well, once I get one child's birth weight, what might be something really easy to do instead of like having to contact households, hoping they respond to me? Well, once I get one household to respond to me, instead of just asking them for the birth weight of their one child, what might I do? Ask them for the birth weight of every child in the household. Well, now some of those observations were dependent on the fact that I got that first child first, right? They were dependent on that I got that household to respond to me. So that's situations where your sample data might violate this assumption. But for everything we'll do in this class, we're going to assume that these observations we have in our data set are independent, okay? So what does the sampling distribution look like? So when we calculate a sample mean, instead of kind of writing this Greek lettering, we'll just kind of use, okay, whatever Y variable I'm looking at, Y bar is going to represent not the population mean, but the sample mean. So all I would do is go through every single person in my sample data, add the values for that variable up, and divide by the number of observations I have. So this looks exactly like what we were doing. The process is the same as what we were doing for the population mean. It's just that I'm not doing it for the entire population. I'm only doing it for the number of observations in my sample. So if I wanted human height, I wouldn't have every single person, say, in the US, but I might have 100 random people. Same process, though, to calculate that mean. And then, so our expected value should be the same. If we're completely choosing people at random, our sample mean should approximately be equal to that population mean. Now, with really small samples, this might not be the case, right? This is the idea that if I were to continue to take sample after sample after sample, the mean of those sample means I'm calculating will always be equal to the true population mean. So if I think about like human height, I don't know what the average human height is. It's probably like 5'9", so what, 68? No, maybe I'm thinking about my height. Maybe it's like 57 inches, right? No, 67 inches, right? Well, if I select only 10 people for my sample, and one of the people in that sample happens to be Yao Ming, if you don't know who that is, it's a basketball player who's very, very tall. What's going to be true about my sample mean relative to the population mean? It's going to be way higher, right? So for small samples, if we only take one, we might not see our sample mean be the same as the population mean. But if I keep on randomly selecting 10 people, I'm not going to get Yao Ming in every single one of my samples, right? If I take enough samples, the mean of those sample means should end up being exactly the same as my population mean. This is what we would call kind of that the sample mean is an unbiased estimator of the true population mean, right? And we'll just kind of use this fact. We won't go through so much the proof, but I think the intuition here goes a long way. Now, I'll use the intuition again and then show you a formula that actually expresses this. But if I were to take a bunch of different samples, right? If I only have 10 people in those samples, what is someone like Yao Ming with an extremely high height? How much is he going to impact that variance? He's going to create a very large variance in that data set. Now, if I randomly select 1 million people, the fact that Yao Ming is in that data set, how much is he really impacting the mean? Not near as much, right? And so as I take samples of larger sizes, what's going to happen to the variance in that distribution that I see for sample means? It's going to get smaller because any one extreme value isn't going to influence that mean near as much. So taking larger samples, it's much more likely I'm going to end up seeing a sample variance that's closer to my population variance. Okay? So what ends up being true is that the variance that we see in these sample means we collected, so let's say I go out and randomly select 10 people, calculate the sample mean. Randomly select another 10 people, calculate the sample mean. I do that 100 times and then look at that distribution of those sample means. The variance of that distribution will be the original variance that existed in the data I was sampling from, but divided by my sample size. So as I take higher and higher sample sizes, what happens to the variation I see in those sample means? It gets closer and closer to. If my sample size goes up, what's happening to this fraction? It's getting, denominator's larger, the fraction gets smaller. If n was infinity, what would this value actually be? 0. So higher sample sizes will reduce the variance that I see from taking these sample means. Why do I like that? Well, because then it doesn't matter if I only have one sample. I know that if I can get a variance on this sample mean to be 0, it doesn't matter who ended up randomly in my sample. I'm always going to kind of see a value that's close to that population mean. Now, when I take really small sample sizes, I might have happened to see a sample mean that was higher than the true population mean. It's much more likely I would see that. Okay, so we're thinking about the variance of our sample means. It's the original variance of the data we sampled from divided by our sample size. So that variance of our sample means decreases as we take higher samples. Okay, so I think I had this. So here's some numbers, and I'm going to use a sample data set. We'll do a little bit of work in Stata here to kind of prove this to ourselves today. We're definitely not going to get as far as I want to. I'm probably taking a little bit longer than I need to, but I want to set us up so we have a base understanding for when we get to harder topics. So let's go here. And let me see. Might not want this file. Let's see what I have here. Yeah, so we're actually going to use another file I put up on Canvas, which was this NBA sample distribution do file. Okay, so I'm going to open this up. Another file I gave you, hopefully. So I had this NBA height data. So this is where, moving forward, we're not going to mess around with like importing Excel files. I'm just going to give you the Stata data right away. We've already seen that I can import a file and save it as a Stata data set. So I'll just start giving you the Stata data sets. So here's my kind of global path. Once again, yours is going to be different. Yours might simply be you're dragging and dropping everything into one folder, right? So I set my global path here. I'm then going to open up that NBA height data, right? So hopefully ahead of class, since I gave you, since I gave you those files, you kind of already had that NBA height data in your OneDrive. We can now use that do file that was kind of looking at sample distributions and open that up. Okay. Any questions on that idea? So once again, I'm just giving you the Stata files already, so we don't have to worry about importing. You can just file open. Okay. So I'm just going to keep two variables because I don't really care about any of the other ones for the sake of this example, right? So I now just have all of the population data. So from one season, I have every single NBA player and their height, okay? So I have the population data. What I can do is then summarize that variable. And what Stata should tell me is what is the mean of the population and what is that variance of the population. So I'm just going to write these down because this I can't save anywhere, right? So this is where we said, like on that first problem set, if I asked you for the population mean and I asked you for the population variance, unless you create variables that were equal to that, if you just use the summarize command, you can't save that into your do file. So I would use comments using this double backslash and say, when I use that summarize command, what I found was the population mean was what? 79.14, and that population variance is 12.59. Okay. So we're okay up to this point, how I would find from a population data set, I could use Stata to calculate my mean and variance. So I'm then going to do something where I'm going to show you the power of Stata, but I am not going to expect you to do this. Okay. I'm just using this to kind of reaffirm what we've talked about. So you can do something in Stata, kind of similar to R, if any of you have used that, where you can create your own programs. Okay. So I'm going to clear out any of the existing programs just in case there's some that are built into Stata that might have the same name that I used. Likely won't be the case, but just in case, right? Once again, I'm not going to make you reproduce something like this. Okay. So I have this program, and what it does is it opens up that original population data. It randomly samples 10 players. It then calculates the sample mean of that height, right, and saves it. It's then going to go through this, and I've got it set to do that 1,000 different times. So I'm going to have 1,000 different samples and calculate the mean from each one of them. So if I'm doing that, you know, for any one sample, I can think about now, I don't just have the distribution of a variable. What I'm now going to be concerned with is I'm calculating sample means. Now, when I happen to take 10 random players, maybe sometimes I see values that are really small. For some of those samples, I see values really large. But what would be the most common values I see? The values that are around whatever that true population mean is. So what's going to end up being true, if I take samples that are large enough, whatever that true population mean is, my sample means will be normally distributed around that, right? It's going to be likely that most of the samples I take, I see values really close to that population mean. Now, for some of them, they might end up with these Yao mean characters that greatly influence the mean, and I'll see really high or really low values, right? But what should be true is if I continue to take samples over and over, the distribution of those sample means should be centered around that true population mean. So I can prove this to you with data as opposed to just going through mathematical proofs, right? So I'm going to define this program. I'm going to run it 1,000 different times, okay? So once I do that, I'm then going to have all those means saved. So before I use the summarize command, I'll just run this program to kind of show you what I'm doing here. And hopefully this doesn't take too long, right, given our Wi-Fi in here. Okay, so it ran this. So what do I now have? Instead of individual player data, I now have 1,000 different sample means, okay? So how could I look at the distribution based off what we've talked about? How could I look at the distribution of those sample means? What's a command that we use to just get a quick look at the distribution? that histogram, right? That hist command, right? So if I want to do this, and I think the variable that I had saved in the data was, what did I call? I called it means, right? So if I want to look at, oh, I want my do file. There we go. I want to look at the distribution of those sample means. I'm just going to use that hist command. This should give me, oh, what does this look pretty similar to? A nice normal distribution. My sample means end up being normally distributed, and around what value? What should be the center of this distribution? The true population mean, which we wrote down earlier, was right around 79. Okay, so this kind of proves this concept or this rule to ourselves with data, right? Oh, it's freaking out at me, so I'm going to close this. Okay, now what should the mean of all those sample means be? We said if we take enough samples, the mean of those sample means should always be the true population mean. So I've got these 1,000 different sample means. If I use the summarize command, that will give me the mean of those sample means. Sure enough, it ends up being 79.14, which is exactly what we found as the population mean. Okay. So if I can take enough samples, that distribution of those sample means will be centered around the true mean, or true population mean, I should say. Now, I also told you that these sample variances, when I'm looking at the variance of those sample means, it should be the original population variance over n. Now, I chose 10 because here, I forget, was this like 12.59? We looked at it before and we wrote it down. We'll see it in the do file in a second. Well, if I take samples of size 10, what should the variance of those sample means be? About 1.259. Okay. So we'll go back and make sure I had that value correct. So what did we say that variance was earlier? 12.59. Okay, I remembered correctly. That's good. My brain's not devolving too much with age. So if I summarize this, what variance do I get for those sample means? It should be 12.59 divided by 10, or approximately 1.259. Now notice, this is a little bit off, right? If I wanted to actually prove this theory, the math side of it, to myself, I wouldn't need 1,000 samples. Technically, I would need an infinite number of samples. So we can't actually do that with the data, right? We know that if we could, the distribution, that variance of our sample means, will be the original population variance over the sample size, right? But if I only take 1,000, it's going to be really close, but it might be a little bit off, like to the second decimal. So here we were off to the second decimal, right? But pretty close to being able to prove this to ourselves with data. Now, if I do the exact same thing, but I take samples of size 30, what should the mean of those sample means be? Still the population mean. But what should happen to the variance of those sample means? If the variance of my sample means is the original variance divided by the sample size, when the sample size went up, the variance on those sample means should go down, right? So when I take larger samples, I'm going to run this same program 1,000 different times. Once I do that, I now have my new sample means from samples of size 30 instead of 10. When I summarize that, sure enough, I end up with really close. Once again, it's going to be off sometimes to the second decimal, but the mean of those sample means is basically that same population mean of 79.14-ish. Now, what happened to the variance? Instead of 1.2 or 1.3, it's now only 0.4, right? It's much, much smaller, right? And if I wanted to continue this thought experiment, what if I took samples of size 100? What is that variance going to get even closer to? 0. Heard someone say it. So sure enough, I go and do that. Takes a little bit longer. Oh, sorry. I not only looked at sample size of 100, I might have broken the computer here. I accidentally had 10,000 instead of 1,000 samples here. So this is going to take way longer. We'll see if, there it goes. Okay. Sure enough, my variance is getting even smaller, even closer to 0 than it was before. So this is just kind of a nice, unique example where we can prove some of these rules that we're talking about, the mathematical proofs. We can prove it to ourselves with data. Okay. Once again, I won't make you reproduce something like this where you have to generate these random samples. I'm just using that to kind of support what we were saying. Oops, sorry. What we were saying about the mean of our sample means and the variance of our sample means. Okay. And to kind of show you the power that Stata has. Okay. All right. Where do I want to get to today? So we're definitely not going to have time to get through all of hypothesis testing or confidence intervals. So I think what I'm going to do is just try to get as far as we possibly can. We'll take a look at that quiz in a second. So when we were looking at these different sample mean distributions, as I look at higher and higher sample sizes, if I'm thinking about the distributions I saw from those like 1,000 different sample means, originally, when my sample size was 10, here was the distribution of my sample means, right? I don't know, its variance was something like what, 1.25 or something like that. When I took samples of size 30, the variance was getting smaller. So what does that mean about my distribution? It's going to be more peaked. Smaller variances mean that more of the data is centered around whatever that mean value is. And then when I took samples of size 100, right, it got an even lower variance. So that's going to be even more peaked. Okay. Okay. Right. So this is kind of a visualization of what's happening to the variance in our sample means. It's getting smaller and smaller as we take larger and larger sample sizes. Okay. Any questions on this idea? Okay. So if I were to standardize this variable, let's say I was looking at the exact same value for my sample mean. So in this example, let's say it was, I don't know, what's the probability that it's greater than 80? Well, notice what's the area under my curve, but to the right of 80 when my sample size is 10? It's like this entire area here. What's the probability I see a sample mean of 80 when I take a larger sample size? It becomes even smaller. And then what about if I take an even larger sample? That same value of 80, the probability is like really, really small. So when I take higher samples, what's the probability I see extremely large values for my sample mean? It starts to go down, which is a good thing. If I'm really interested in like the average score of a student in my 371 class and I only have a random sample, I want to make sure that the probability I see something further from that true mean is really small. So what can I do? Get as large of a sample as possible. Okay. The larger the sample I get, the probability I see these really extremely large values for my sample means start to get lower and lower. Okay. I started to draw this too. We can just kind of focus on what I had here. Just can ignore this. Okay. So yeah, what, 15 minutes? So we looked at these sample distributions. They were a little bit off, right? So we can kind of see as I take higher samples, the difference between what the true population values would be in those samples is going to be different, right? Because the size of that sample was impacting the size of my sample variance. So if I tried to create, let me see if I have it here. There we go, right? So if I tried to create z-scores, what was I using? I was using my variant. I was dividing by my standard deviation in that denominator. But my sample variances are going to be a little bit off of that population variance. So when I try to create a z-score, using those means I see from and the variances I see from my sample data, it should be that I was doing something like this. So just like I can create a z-score for a value for some random variable, I can calculate a z-score for my samples, right? So just instead of x, we're now looking at what's the z-score of seeing this one specific sample mean. Now, ideally, we would subtract the true population mean of that variable x, and we would divide by the standard deviation. Sorry, not x. We're looking at the mean now, so x bar, right? The problem is I don't have the population data. So really what we're doing is we're taking different values for the sample mean, we're subtracting the true population mean, but we're dividing by the sample variance, or sorry, I shouldn't say sample variance. We're using the sample variance to calculate that sample standard deviation. So we won't end up with z-scores because we know that if I were to look at the entire population, there's going to be a specific amount of variance in that data. If I have a smaller sample, we said the variance is going to be larger because any one observation might influence the mean a little bit more. So I know that this is always going to be greater than the true population variance. The sample variance will always be greater than the true population variance, or the sample standard deviation is always greater than the population standard deviation. Okay? So I know that I'm not going to get exactly what that z-score should be. In fact, what we'll say is these are actually coming from what we call a student t-distribution. It's very similar to the standard normal. It's just going to be a little bit more spread out. It's going to have a slightly higher variance. So just like when we were saying, oh, if it's a little bit more spread out, then looking at the same value for the mean, we're going to have different probabilities. They won't be exactly what we would have found from that standard normal. So instead of using the standard normal tables, we have to use these t-tables. And every probability is a different distribution, so it depends on our sample size. It gets a little bit complicated to use, but for the sake of this class, instead of using these student t-distributions, so I'll skip ahead here, where each student t-distribution, for lower sample sizes, we come up with this thing called degrees of freedom. They're going to be a little bit small. Well, ultimately, we don't have to worry about this, right? As long as we can get a sample size, skipping back and forth a little bit, as long as I can get a sample size above 30, it doesn't even matter if the original data was Norman distributed. I'll essentially get, when I calculate the standardized variable, my student t distribution will be very close to what that standard normal distribution is. In fact, technically, to get them to match up, my sample size would have to be infinity. But once I get to be above 30, like even out to like the fourth decimal, those probabilities will be the same. So instead of worrying about using the standard student t, we can just always use that standard normal distribution. And most data sets we have from the real world are going to be way above 30, right? So this is just kind of, if I were to go through that process, instead of using human height from like that MBA, if I was to use any other variable, it doesn't matter what the original population variable is distributed like. It doesn't even have to be normally distributed. In fact, I could have like some really weird original distributions. And if I take samples of higher and higher sizes, notice those sample means by the time I get to 30, these are really close to what looks like a normal distribution. And in fact, over 30, not only are they a normal distribution, as I get to higher and higher sample sizes, they'll be approximately the standard normal distribution. So instead of worrying about, I'll skip through this pretty quick. I don't really need to spend a lot of time on this because we're not going to use this. Instead of using these student t-tables, we know that as long as we can get a sample size above 30, we can actually just default to using our standard normal. Now, the reason why I'll show you the student t-table here in a second is because if I could get an infinite sample size, my student t distribution will be the same values I could find from that standard normal, right? So notice like before we had like 1.29 and we go back, we'll kind of see these are the same values I would find from that standard normal. So I put the student t-tables up on Canvas. If I get sample sizes over 30, in fact, probably want a little bit higher than 30, but just to kind of prove this to you, if I look at these values where my sample size is infinite, I would find the exact same values I could find from a standard normal. So for example, if I want a probability of 0.025 in my tail, if I looked at the infinite value, this should be the same value I find from the standard normal. So if I want, that 0.975, that's the probability I want. If I find it, sure enough, what z-score gives that to me? 1.96. That's the same as wanting that 0.025 probability, same as the t value would be. So as the sample size gets larger, our student t distribution basically becomes the standard normal. So we're going to be a little bit off when we use the standard normal if we don't have like really large data sets. If it's anything over 30 though, we're going to be so close, like out to the third or fourth decimal, we'll just use that standard normal to approximate. Okay, so that's why I skipped through the student t slides very quickly. We're ultimately going to not really end up using them. Now, one thing that's kind of nice, so when we do it by hand, we're going to use that standard normal. Once we get to doing more work in Stata, it actually reports to us the exact student t value. Like it uses the student t distribution behind the scenes for us. We're not actually getting an approximate value. It's actually using the correct student t distribution. Okay. But for any work that we do by hand, sample size is over 30, we can use that standard normal to approximate. Okay. So based off of where we're at, we didn't quite get to hypothesis testing. So I think what I'm going to do is the last 2 questions on the problem set are related to hypothesis testing. I know for sure that we're going to get through that on Tuesday, right? So you can work up to the problem set through those first 8 questions. Those last 2 questions shouldn't really take you a whole lot of time once we work through it on Tuesday, okay? So I would start working on that problem set now if you already haven't. You should be able to work up to, based off what we talked about, up to that 8th question. The remaining 2 questions, you should be able to answer next week after Tuesday's class. So you'll have Wednesday, Thursday, and Friday to complete those final 2 questions, okay? Now for the quiz, that's going to have some questions on hypothesis testing and confidence intervals. So I'm going to push that due date off to be not next Friday, but the following Tuesday at the end of the day. Okay. I'm guessing after Tuesday's class, we'll have talked through all the hypothesis testing stuff and likely the majority of confidence intervals, right? So we should be able to cover all of that in Tuesday's class. And then next Thursday, we'll start something called linear regression, okay? So if you're studying for that quiz, if you see the hypothesis testing confidence interval questions, we won't cover that until after Tuesday's class, okay? Does that make sense what I'm saying? So the problem set due date is going to stay the same, and you're only going to have 3 days to complete those final 2 questions. The quiz, the first quiz, I'm pushing the due date up to be not next Friday, but the following Tuesday. And there, we should have covered all the material after Tuesday, so you still should have a week to review all of these practice problems. You could start reviewing the vast majority of them now, right? But the last, I don't even know, I'd have to look at exactly how many, maybe 4 or 5. That's what we'll be kind of covering on Tuesday. So we've got hypothesis testing, confidence intervals. I'll post the module 3 slides. I'm basically going to just grab what we haven't covered for module 2 and kind of start there. But for being in class today, we come down here, we look at this class, in-class quiz 1. So this is where sometimes I want the value of class there to be value added and attending. So if we're looking at these questions, these are covering confidence intervals. We haven't talked about that yet, right? So what I'm going to do, actually, I should have had this set up a little bit differently, but I'll change this kind of moving forward. You can kind of see what these values should be, right? So if I preview this, I have kind of these type your answers in. I think if you are, is it prompting you for the code for today? 2.13. So this is usually how you would get into the in-class quizzes. I give you that code that lets you in, okay? Now, we haven't covered this material, but to give you credit for being here today, and we might review these during Tuesday's class, the answer to those questions, oh, now I exited out of it for me, of course. So go back to them. I'm telling you the answers should be, this is where if you're paying any ounce of attention and you're in class, you should get this correct. If you weren't in class and you somehow guess these values, holy cow, right? So 97.62 and 106.38 should be the answers to that first question, okay? We'll work through this once again on Tuesday's class after we've talked a little bit more about confidence intervals. And then if we wanted to do some hypothesis testing, what levels can we reject certain values at? We'll talk about this on Tuesday's class as well. the answer to question 2 should be only the 10% level. I also have kind of 3 set to be just yes, do you earn the base points for being here today? I'm going to adjust some things on Canvas that we don't have to have that base point question. I thought I got rid of it on this quiz, but I forgot to. So for the sake of what you need to do, 97.62, 106.38 are the answers to that first question, 10% only, the answer to the second, and then just click this yes button, okay? If for some reason you forget to have a way I can like see that you submitted the quiz in class, I can see that you got the other 2 questions right, but those will be the values that get you the full points, okay? So, yeah. Okay, so give me 1 second. So just a couple more minutes, maybe another minute of your time. So tomorrow I'm going to have additional office hours since I didn't have office hours Monday from 8 to 10. I can't stress enough. If you have not started on that first Stata problem set and got a Stata working, I would highly suggest stopping by office hours tomorrow. I expect to have office hours on Monday, but what's supposed to happen this weekend? Crazy weather, right? So I don't know what Monday is going to look like, and I don't know what my office hours might happen to them on Monday if the weather's too crazy and people aren't able to kind of drive around Bloomington. My experience, people down here don't know how to drive in the snow, okay? So make sure you try to get Stata working. If you still are having issues, tomorrow's office hours are a good time to do that. I'll be here the majority of the day, so if for some reason those office hours don't work and you want to stop by sometime in the afternoon, send me an email and we can likely find a time to make that work. Even if it's not in person, it's via Zoom. Also, keep an eye out on Canvas announcements. If I do end up not having office hours on Monday because of weather, I likely might still host virtual office hours, okay? Other than that, a fun, safe weekend. Stay warm this weekend, and I will see you on Tuesday, okay? Give me 1 second here.